Imagine a world map with no Atlantic Ocean, no Pacific Ocean, no scattered continents. Instead, all the land on Earth is fused into one colossal mass, stretching from one horizon to the other. This was Pangaea, the supercontinent that existed roughly 300 million to 180 million years ago, a chapter in our planet's history when geography, climate, and life itself were unlike anything we know today. The story of Pangaea begins deep in geological time, shaped by forces far beneath our feet. The Earth's crust is not a single solid shell, but a mosaic of giant slabs called tectonic plates. For hundreds of millions of years before Pangaea formed, these plates drifted slowly over the mantle, carrying continents like rafts across an ocean of rock. They collided, split apart, and collided again in a repeating pattern geologists call the supercontinent cycle. Before Pangaea, other giant landmasses such as Rodinia and Pangaea had risen and broken apart, each leaving behind a different arrangement of seas and continents. By the late Paleozoic era, the pieces of Earth's scattered lands began converging. North America, South America, Africa, Europe, Asia, and smaller continental fragments moved toward one another, closing ancient oceans in their path. When these colossal blocks of crust met, they did not simply stop. They crumpled, folded, and thrust upward, creating mountain chains that still exist today. The Appalachian Mountains in North America and the Atlas Mountains in Africa are among the relics of those collisions. The result was extraordinary. Nearly all of Earth's land gathered into a single supercontinent surrounded by an enormous global ocean called Pangaea. Along one side of Pangaea lay the smaller Paleotethys Sea, a remnant of earlier waters. On land, the distances were vast beyond anything in our modern world. A traveler could walk from what is now Alaska to what is now South Africa without crossing a sea. This unification of land reshaped every part of the planet's systems. Winds and ocean currents flowed differently without familiar coastlines to deflect them. Rainfall patterns shifted. Deserts grew in the immense continental interior, far from the moderating influence of the sea, while coastal regions flourished in wetter, milder conditions. Plants and animals spread freely across the supercontinent, erasing the natural barriers that oceans impose today. To understand Pangaea is to understand how Earth's surface is never fixed. It is a restless, living mosaic. The same forces that built this supercontinent were already preparing to tear it apart, setting the stage for the continents we know today. Imagine looking down at a map of the Earth and finding no Atlantic, no Pacific, no scattering of continents across a blue planet. Instead, you see one continuous sweep of land stretching from horizon to horizon, an immense solid shape surrounded by a single, endless ocean. This was Pangaea, a supercontinent that existed from roughly 300 million to 180 million years ago. For tens of millions of years, it dominated Earth's surface, shaping climate, ecosystems, and the course of life itself. Pangaea was not a random arrangement of land. It was the product of deep, slow forces working far beneath our feet. The movement of tectonic plates. Earth's outer shell is divided into massive slabs of crust that float on the molten mantle below. These plates drift at only a few centimeters per year, but over millions of years their collisions, separations, and sideways shifts completely rearrange the face of the planet. Continents can be torn apart, pushed together, or even fused into one colossal landmass. The merging of Earth's continents into Pangaea was part of what geologists call the supercontinent cycle, a repeating pattern in which scattered landmasses come together, remain united for millions of years, and then slowly break apart again. Before Pangaea, earlier supercontinents such as Rodinia and Pangaea had formed and split, leaving their fragments to drift across the globe. Each of these earlier worlds looked different, but all were part of the same slow geological rhythm. By the late Paleozoic era, the pieces of Earth's crust were on a collision course again. North America, then called Laurentia, moved toward northern Europe and parts of Asia. To the south, the vast continent of Gondwana, holding what is now South America, Africa, India, Australia, and Antarctica, was drifting northward. Smaller landmasses and island arcs lay between them, caught in the shrinking ancient oceans. Over tens of millions of years, these oceans, including the Reich Ocean, narrowed until they disappeared altogether. The collisions that built Pangaea were anything but gentle. When continents meet, the crust is forced upward, creating mountain ranges on a monumental scale. The Appalachian Mountains in North America and the Atlas Mountains in Africa are among the weathered remnants of those ancient upheavals, once likely as tall as the modern Himalayas. These mountains became landmarks of a new Earth, marking the seams where continents had fused. By the early Permian period about 299 million years ago, the process was complete. Nearly all of Earth's land had gathered into one vast shape, Pangaea, surrounded by the enormous Pangaea Ocean. Along its eastern margin lay the Paleotethys Sea, a remnant of earlier waters, but the variety of smaller oceans and seas that define our modern world did not yet exist. This new geography transformed the planet's systems. With no major oceans to break it apart, wind could sweep across Pangaea for thousands of kilometers without obstruction. Ocean currents in Pangaea moved in vast, uninterrupted loops, redistributing heat around the globe in patterns unlike any today. Rain-bearing winds rarely reach the supercontinent's deep interior, leaving it arid and extreme in its seasons, while the coasts were milder and wetter. Life responded to this connected world in ways impossible today. Without ocean barriers, plants and animals could spread freely from one side of the supercontinent to the other. Fossils of identical species are now found on continents separated by oceans, proof that they once walked the same land. Ecosystems were immense, predators and prey ranged widely, and evolutionary pressures played out on a global stage. Yet Pangaea was not permanent. Even as it stood united, the forces that had built it were preparing to break it apart. Heat and pressure built beneath its seams, cracks began to form, and volcanoes erupted along the fault lines. Over tens of millions of years, those cracks would widen into new oceans, and Pangaea would fragment into the continents we recognize today. To understand Pangaea is to see the Earth as it truly is, not fixed and unchanging, but alive and in motion. Its story is a reminder that the continents beneath our feet are only temporary arrangements, shaped by forces that never rest. Pangaea was just one chapter in that ongoing story. But during its reign, it created a world unlike any we have ever known. The making of Pangaea was not the result of a single cataclysm, but of a chain of slow, relentless events unfolding over hundreds of millions of years. To see its beginning, we have to turn the clock back well before the supercontinent itself existed, to a time when Earth's land was scattered in many smaller continents adrift on an ancient global ocean. The continents of the late Paleozoic were not arranged like the familiar map in our minds. In the north, Laurentia, the ancient core of North America, floated near Baltica and Siberia. In the south, stretched Gondwana, a giant in its own right, containing South America, Africa, India, Australia, and Antarctica. Between them lay wide oceans, including the Reich Ocean and the shrinking Iapetus Ocean, separating these great landmasses. The driving force behind their motion was plate tectonics, the slow movement of the rigid plates making up Earth's crust. These plates, riding atop the semi-fluid mantle, were in constant motion, colliding, sliding past one another, or pulling apart. Over immense spans of time, these movements drew the continents together, closing the oceans between them. This is part of the supercontinent cycle, a repeating pattern in which landmasses merge into a single supercontinent, then fragment and drift apart again. The first major step toward Pangaea was the collision of Laurentia and Baltica, around 400 million years ago during the Caledonian orogeny, a mountain-building event that created high ranges across what is now northern Europe and northeastern North America. This fusion formed a new combined continent called Euramerica, or Laurussia. Meanwhile, Gondwana was drifting northward. Its sheer size meant that, as it approached Laurussia, smaller fragments, island arcs, and microcontinents were caught between them. These were gradually swallowed up in a series of collisions, each one lifting new mountain ranges and leaving deep scars in the crust. Among these scars were the foundations of the Appalachian Mountains in eastern North America and the Anti-Atlas Mountains in Morocco. By about 320 million years ago, the Reich Ocean had almost disappeared. The collision of Laurussia with Gondwana during the Alleghanian orogeny closed the gap entirely. This was one of the great tectonic events of Earth's history, locking nearly all the world's land together into a single connected mass. Only parts of Asia and Siberia remained separate for a while longer. The final act came as Siberia and other northern terrains drifted in and collided with Laurussia's eastern side. This closed the last major oceanic gaps and left Pangaea nearly complete. By the early Permian period, roughly 299 million years ago, the supercontinent stretched almost from pole to pole. The formation of Pangaea had dramatic consequences for the planet's geography and climate. The collisions produced vast mountain ranges, some likely rivaling the modern Himalayas, that towered over the surrounding plains. These mountains influenced wind patterns, redirecting moist air towards certain regions and casting others into rain shadows, helping to create the massive arid zones that would dominate Pangaea's interior. The closure of ancient oceans also altered the planet's ocean currents. With a single immense landmass in the surrounding Pangaea Ocean, water could circulate in massive, uninterrupted gyres. Along Pangaea's eastern side, the smaller Paleotethys Sea lingered, a remnant of earlier marine systems, providing sheltered environments for marine life even as the open ocean remained vast and deep. Volcanic activity was common along the suture zones where continents had fused. Magma welled up from deep in the earth, feeding volcanic arcs and lava flows that reshaped local landscapes. These eruptions released carbon dioxide into the atmosphere, contributing to greenhouse conditions, but also deposited mineral-rich ash that nourished plant life in the years following. By the time Pangaea stood complete, it was more than just a new arrangement of continents. It was a fundamentally new Earth system. Land, sea, and sky behaved differently. Ecosystems, once separated by oceans, now connected in vast networks. Species could migrate across thousands of kilometers, encountering new habitats and competitors. Mountain chains, deserts, wetlands, and forests were all part of one colossal continuous landscape. This unification marked the beginning of one of the most remarkable chapters in our planet's history. Pangaea would shape the evolution of life, influence the chemistry of the atmosphere, and leave geological fingerprints still visible today. Yet, as immense and seemingly permanent as it was, Pangaea was only a temporary arrangement, a moment in the endless cycle of assembly and breakup that defines the restless nature of Earth's surface. When Pangaea stood complete, it was not simply a continent. It was an entire world bound together. Its shape stretched in a rough sea, with the open space of the Paleotethys Sea caught inside the curve and the immense Pangaea Ocean surrounding everything else. From polar ice in the far south to warm equatorial forests and deserts, its landscapes were as varied as they were vast. One of the most striking features of Pangaea was its sheer size. At its widest points, the land extended more than 12,000 kilometers. This scale created a dramatic contrast between the coasts and the interior. Along the edges, the influence of the surrounding ocean brought humidity, moderate temperatures, and abundant life. In the deep interior, far from the reach of moist winds, lay some of the largest deserts in Earth's history. The coastal regions were dynamic environments. Warm, shallow seas lapped against wide continental shelves, creating tidal flats, wetlands, and lagoons. In some places, rivers carried sediments from distant mountains, forming fertile deltas where forests thrived. Other coastal zones were shaped by strong monsoonal winds, which brought heavy seasonal rains followed by drier periods. The consistent interaction between land and sea supported lush vegetation, seed ferns, conifers, horsetails, and a rich variety of animals. Moving inland, the landscape transitioned into broad plains and savannas. These intermediate zones formed the middle ground between the coasts and the interior deserts. Grass-like plants and scattered forests dotted the terrain, and rivers winding from the mountains toward the sea provided natural corridors for life. Many animals, from early reptiles to large synapsids, likely traveled these plains in seasonal migrations, following the availability of food and water. In the interior heartlands, the conditions changed dramatically. Here, the distance from the sea was so great that most moisture was lost before it could reach the center. The result was a climate of extremes: scorching summers, freezing winters, and little rain. Vast red deserts, colored by iron-rich sediments, spread for thousands of kilometers, broken only by rocky uplands or occasional river systems. These deserts were unlike anything today. Even the Sahara or Gobi are small by comparison. Life here was sparse, adapted to survive long droughts and sudden, short-lived floods. Pangaea was also defined by its mountain ranges, the scars of the collisions that formed it. The central Pangaean mountains stretched across what is now eastern North America, northwestern Africa, and parts of Europe, a massive chain formed by the joining of Laurentia and Gondwana. To the north and east, other ranges marked where smaller land masses had been welded on. These highlands shaped wind and rain patterns, creating rain shadows and influencing the spread of deserts and forests alike. Rivers were lifelines across the supercontinent. Some began in the high mountains, carving deep valleys before spilling into the lowlands. Others meandered slowly across broad plains, sometimes for thousands of kilometers before reaching the sea. Because Pangaea was unbroken, these rivers often crossed what today would be multiple continents. They carried nutrients from the mountains to coastal wetlands, linking distant ecosystems into one vast web. Along its eastern curve, the Paleotethys Sea formed an inland marine environment sheltered from the full force of the Pangaea Ocean. This sea provided rich fishing grounds, coral reefs, and warm, shallow habitats for marine life. It also acted as a climatic buffer, moderating conditions in the regions around it. From above, had anyone been there to see it, Pangaea would have been a patchwork of environments. Polar ice sheets in the far south, tropical belts straddling the equator, vast interior deserts, fertile river valleys, mountain chains, and rich coastal forests. But all of it was connected. There were no continental barriers, no ocean crossings, no isolated landmasses. The geography of Pangaea was one continuous interlinked system where changes in one region could ripple across thousands of kilometers. This unity gave Pangaea a character unlike any modern arrangement of continents. It was a place where deserts could feed distant forests with wind-blown dust, where rivers could carry sediments across half a continent, and where animals could roam from tropical coasts to high mountain valleys without ever encountering a sea. It was a world of extremes, yet also of connection, a single continent that contained nearly every type of landscape Earth could offer. Pangaea's immense size gave it a climate unlike any other era in Earth's history. With almost all the planet's land fused into one mass, the usual influence of oceans, which today moderate temperatures and bring rainfall deep inland, was limited to the supercontinent's outer edges. The result was a world of sharp contrasts, humid, life-rich coasts, and a vast, arid interior where the seasons swung between extremes. Along the coasts, the surrounding Panthalassa Ocean and the Paleotethys Sea acted as climate buffers. Warm ocean currents brought moisture-laden air ashore, feeding dense forests, swamps, and wetlands. Seasonal monsoon winds, driven by the heating and cooling of the vast landmass, dumped heavy rains during wet seasons and left shorter dry periods in between. These coastal belts had some of the most stable and productive climates of the age. But the further one moved inland, the more the ocean's influence faded. In the continental interior, moisture rarely penetrated. Rain clouds often released their water before reaching the center, leaving behind air that was hot and dry in summer and cold and clear in winter. This isolation produced deserts on a scale unmatched today. These interior arid zones were not only dry, but also subject to wide temperature swings, baking heat under the summer sun, then frigid nights or winters due to the absence of cloud cover in nearby seas. Pangaea's shape and position also played a role. Much of the continent straddled the equator, creating broad tropical belts with intense solar heating. This heating powered strong atmospheric circulation. Rising warm air near the equator triggered heavy rains in some zones and pushed dry air toward the subtropics, where it descended and intensified the desert climate. At higher latitudes, closer to the poles, cooler conditions prevailed, and parts of southern Gondwana even supported ice sheets during certain periods. The atmosphere's composition shifted significantly during Pangaea's lifetime. In the late Carboniferous, oxygen levels may have reached around 30%, much higher than today's 21%. This allowed insects and arthropods to grow to enormous sizes, with dragonflies nearly a meter across and millipede-like arthropods stretching several feet long. As the Permian period progressed, oxygen levels fell to perhaps 15%, favoring species adapted to lower oxygen environments and contributing to the decline of these giants. Carbon dioxide levels were also high at times, fueled in part by volcanic eruptions along Pangaea's tectonic seams. CO2 trapped heat, intensifying greenhouse conditions and driving powerful weather systems. Periods of intense volcanism could raise global temperatures, while massive eruptions releasing sulfur aerosols could temporarily cool the planet by reflecting sunlight back into space. Wind patterns were more direct than today, sweeping across thousands of kilometers without interruption from scattered continents. Dust from the dry interior could travel immense distances, fertilizing coastal soils and even enriching marine ecosystems. Storms, too, could grow to enormous sizes, carrying the energy of an unbroken atmosphere. Pangaea's climate was a system of extremes and connections. Wet coasts feeding lush ecosystems, dry interiors testing life's limits, and winds and currents linking them in a global loop. This unique combination of geography and atmosphere set the stage for the evolution, adaptation, and eventual transformation of life across the supercontinent. The land of Pangaea was a mosaic of environments, from humid coastal forests to the scorching deserts of its interior, and life adapted to each in remarkable ways. The absence of ocean barriers allowed plants and animals to spread freely across the supercontinent, creating ecosystems that spanned thousands of kilometers. Evolution on Pangaea played out on a continental scale. Along the coasts and river valleys, forests flourished. Towering conifers, broad-fronted seed ferns, and dense stands of horsetails and club mosses formed thick green canopies. The humid air supported a wealth of amphibians, salamander-like creatures and massive crocodile-like predators that lurked in swamps. Insects ruled the skies and forest floor, some reaching giant sizes thanks to higher oxygen levels earlier in Pangaea's history. Dragonflies with wings nearly a meter wide hunted over the water, while enormous millipede-like arthropods crawled through the leaf litter, recycling decaying plant matter into the soil. Sharing these forests were the first truly terrestrial reptiles, freed from the amphibians' dependence on water for reproduction. The amniotic egg, protected by a shell and internal membranes, allowed reptiles to lay their eggs on land, opening up habitats far from rivers and wetlands. These reptiles ranged from small, insect-eating diapsids to larger herbivores that grazed on tough plant material, Among the most successful land animals were the synapsids, often called mammal-like reptiles. Some were carnivores, like the sail-backed Dimetrodon, which may have used its tall spinal sail to regulate body temperature or display dominance. Others were stocky herbivores, like Edaphosaurus, with barrel-shaped bodies for digesting fibrous plants. As the Permian period progressed, more advanced synapsids known as therapsids appeared, showing features, upright limb posture, differentiated teeth, that hinted at their eventual descendants, mammals. Farther inland, in the arid heart of Pangaea, life took on a different character. Vegetation was sparse, consisting of hardy, drought-resistant plants, such as cycads, ginkgos, and scrubby conifers. Animals here were adapted to conserve water and endure temperature extremes. Some reptiles evolved thick, scaly skin to reduce moisture loss. Others burrowed underground to escape the heat. Herbivores in these regions were mobile, often traveling long distances in search of seasonal greenery, while predators followed these herds across the open plains. The intermediate grassland and savanna-like zones between coasts and deserts were highways of life. Rivers and seasonal streams provided water, drawing both herbivores and carnivores. These corridors allowed species to move between regions, maintaining the genetic flow that kept populations connected across vast areas. Predator-prey relationships were dynamic across Pangaea. Large carnivorous therapsids like gorgonopsids were apex predators in many regions, using speed and saber-like teeth to hunt down herbivores. Smaller predators preyed on amphibians, insects, and juvenile reptiles, filling the ecological gaps. Because Pangaea was a single landmass, these creatures were not confined to isolated continents. Fossil evidence shows identical species in what are now South America, Africa, and India. This freedom of movement created ecosystems with enormous geographic reach. A single predator species might range from one end of the supercontinent to the other, adapting to different climates along the way. Life on Pangaea was not static. Shifts in climate, volcanic eruptions, and slow geological changes continually reshaped the environments. Species adapted, migrated, or disappeared, but the land always remained alive with movement, competition, and the endless interplay between plants and animals. The story of Pangaea's land life is one of resilience and innovation, laying the evolutionary groundwork for the world that would follow when the supercontinent finally broke apart. While Pangaea's land was vast and varied, the oceans that surrounded and bordered it were no less important to the planet's story. The great global sea of the age was Pangaea, a single, almost limitless ocean that covered most of Earth's surface. From the shores of Pangaea, Pangaea stretched unbroken to the horizon in every direction, a boundless expanse where waves and currents moved on a planetary scale. Circulating around the supercontinent, Pangaea's currents redistributed heat from the equator toward the poles. Without the interruption of modern continental shapes, these oceanic gyres were massive and steady, influencing climates far inland. The warm waters feeding Pangaea's coasts supported diverse marine ecosystems, while cold currents brought nutrients up from the deep, enriching surface waters in other regions. Along Pangaea's eastern curve lay the Paleotethys Sea, smaller and more enclosed than Pangaea, but just as important. Sheltered by the arms of the continent, it provided calm, warm, shallow waters that served as a cradle for marine life. Coral reefs flourished here, built by early corals and sponges, creating habitats for countless invertebrates and fish. These reefs teemed with life, from small armored fish to sleek early sharks patrolling the deeper channels. Shallow coastal waters around Pangaea's continental shelves were some of the richest environments of the time. Sunlight penetrated the clear, warm seas, fueling blooms of plankton, the base of the marine food web. These microscopic organisms fed swarms of filter-feeding invertebrates, which in turn supported a wide variety of predators. Bivalves, brachiopods, ammonites, and crinoids were common, their shells and bodies littering the seafloor and leaving a fossil record that still endures today. The open waters of Pangaea were home to powerful swimmers, early sharks, large predatory fish, and fast-moving cephalopods. These animals roamed vast distances, following seasonal currents and the migrations of smaller prey. In the deep ocean, little is known of the ecosystems, but even there, life adapted to the darkness and pressure, just as it does in today's deep seas. The oceans and land were deeply connected. Rivers from Pangaea's mountains carried minerals and sediments into the coastal waters, enriching them with nutrients. Winds sweeping across the arid interior lifted fine dust and carried it far out to sea, where it settled into the water and fertilized marine ecosystems. In return, the oceans influenced life on land. The moisture they supplied to coastal forests and swamps was critical for sustaining the lush environments at the edges of the continent. Marine life also faced challenges. Changes in sea level, driven by climate shifts and tectonic movements, sometimes flooded coastal plains, creating temporary inland seas. At other times, the waters retreated, stranding marine organisms and altering entire ecosystems. Volcanic activity and shifts in atmospheric composition could trigger mass die-offs in the oceans, reshaping the balance of life. Yet despite these upheavals, Panthalassa and the Paleotethys Sea remained constant forces during Pangaea's reign. They were sources of abundance, pathways for migration, and regulators of global climate. Together, they formed the watery counterpart to the supercontinent's sprawling land, two halves of a single interconnected world. Pangaea was born from the Earth's restless interior, and the forces that created it never stopped working. Deep beneath its mountains, plains, and deserts, the mantle churned with heat and motion, driving the slow but relentless movement of tectonic plates. This constant activity shaped the land, fueled volcanoes, and at times brought catastrophe to the life that depended on the planet's stability. The seams where Pangaea's continents fused, called suture zones, were reminders of ancient collisions. Here the crust was thick, folded, and fractured, riddled with fault lines where earthquakes could shatter the ground. In some regions, these zones were also volcanically active. Magma rose from deep within the mantle through cracks in the crust, feeding eruptions that could blanket vast areas in ash and lava. Volcanoes were both destructive and creative. Their eruptions could devastate ecosystems, smothering forests, poisoning rivers, and blocking sunlight with ash clouds. Yet, over time, volcanic soils became some of the most fertile on Earth, enriched with minerals that nourished plant life. This dual role, destroyer and life-giver, made volcanism a powerful driver of change on Pangaea. One of the most dramatic volcanic events of this era occurred near the end of the Permian period. The Siberian Traps eruptions. Although technically located in the northern part of Pangaea's landmass, their impact was global. For hundreds of thousands of years, colossal outpourings of basaltic lava covered millions of square kilometers. The eruptions released vast amounts of carbon dioxide, methane, and sulfur gases into the atmosphere, altering climate on a planetary scale. The environmental consequences were severe. Increased greenhouse gases drove global warming, while sulfur aerosols reflected sunlight and triggered short-term cooling. The combination caused climate instability, acid rain, and widespread ocean anoxia, a depletion of oxygen in the seas. These events are closely linked to the end Permian mass extinction, the most devastating biodiversity crisis in Earth's history, wiping out over 90% of marine species and around 70% of terrestrial vertebrates. Even in calmer times, Pangaea's geology was in motion. Mountain ranges continued to rise as tectonic plates pressed against each other. Uplift exposed ancient rocks, which were worn down by wind and water, feeding sediments into river systems and eventually into the surrounding oceans. In the interiors, rift valleys, long depressions in the crust, began to form as tectonic forces subtly shifted from compression to tension, marking the first hints of Pangaea's eventual breakup. Earthquakes often accompanied these changes. In regions where plates ground past one another or slipped along faults, tremors could reshape landscapes instantly, altering river courses, triggering landslides, and fracturing the ground. Through all of this, geological forces and volcanism were the hidden architects of Pangaea's story. They built mountains, created fertile soils, fueled catastrophic extinctions, and began the slow tearing of the supercontinent apart. Pangaea was never truly at rest. Its surface was the living expression of a dynamic planet, constantly reshaping itself from within. For millions of years, Pangaea seemed eternal, a single unbroken landmass dominating the planet. Yet beneath its surface, the same forces that had assembled it were quietly preparing its undoing. The breakup of Pangaea began not with a single dramatic event, but with subtle shifts in the balance of Earth's tectonic engine. The supercontinent acted like an enormous blanket over the mantle, trapping heat below. Over time, this heat built up, increasing pressure in the mantle rocks beneath the thick continental crust. Eventually, that pressure began to find release along weak points, many of them the same suture zones where the continents had been welded together during Pangaea's formation. By the late Triassic period, around 200 million years ago, the first signs of rifting appeared. Long fractures opened in the crust, forming rift valleys that stretched for hundreds of kilometers. Volcanic activity increased along these rifts, as magma rose from below to fill the gaps. These eruptions created extensive lava flows and released greenhouse gases, subtly altering global climate. The initial splitting occurred along what is now the central Atlantic region. The land between modern-day North America and Africa began to pull apart, forming a chain of fault-bounded basins that filled with water from rainfall and early marine incursions. These became long, narrow lakes, rich with life, but also evidence that the continent was beginning to tear in two. Meanwhile, in the southern half of Pangaea, similar stresses began to open rifts between what would become South America, Africa, Antarctica, and Australia. Though these regions would remain connected for tens of millions of years longer, the pattern was set. The supercontinent was breaking into smaller drifting plates. As rifting continued, the Atlantic Ocean slowly began to form. At first, it was nothing more than a narrow seaway, but over millions of years, it widened into a true ocean basin. New crust was created at mid-ocean ridges, pushing the separating continents farther apart with each passing millennium. The breakup had profound effects on climate and ecosystems. As coastlines multiplied, more regions came under the moderating influence of the sea, reducing the vast arid interiors that had characterized Pangaea. Ocean currents shifted, creating new weather patterns and altering global heat distribution. For plants and animals, the fragmentation of land meant isolation. Populations that once mingled freely now evolved separately, beginning the long process of divergence that would eventually produce entirely new species. Volcanism was both a symptom and a driver of this change. Massive eruptions in the Central Atlantic magmatic province released enormous amounts of carbon dioxide, contributing to warming that may have played a role in the mass extinction at the Triassic-Jurassic boundary. This event cleared ecological space, paving the way for the rise of dinosaurs as dominant terrestrial vertebrates in the Jurassic period. By the early Jurassic, Pangaea was no longer a single, seamless continent. It had begun its transformation into the arrangement of continents we recognize today, a process that continues even now, as the plates that once formed Pangaea drift slowly across the face of the Earth. Pangaea's reign as a supercontinent lasted for well over 100 million years, yet in the scale of Earth's history it was only one chapter in a much longer story. Its formation, existence, and eventual breakup reshaped the planet's geography, climate, and living systems in ways still visible today. Though the landmass itself is long gone, its legacy is written in the rocks, the fossils, and even in the arrangement of the continents we now inhabit. One of the clearest legacies of Pangaea lies in its mountains. The Appalachian Range in eastern North America, the Anti-Atlas of Morocco, and other scattered highlands are remnants of the colossal chains that rose when ancient continents collided. Though weathered and reduced over millions of years, these mountains still trace the seams where Pangaea's pieces were welded together. The supercontinent also left its mark in the distribution of species. Identical fossil plants and animals are found on continents now separated by vast oceans, a direct testament to the time when they were connected. The Glossopteris fern, once spread across Gondwana, and the reptile Mesosaurus, found in both South America and Africa, are among the most famous examples. These patterns provided some of the earliest, most compelling evidence for the theory of continental drift. In terms of climate history, Pangaea's existence reshaped the global circulation of air and water. Its immense size produced one of the largest desert systems in Earth's history, while its breakup led to the creation of new coastlines and the establishment of modern ocean current patterns. These changes influenced evolutionary pathways, driving diversification as isolated populations adapted to new environments. Pangaea's breakup also set the stage for the modern arrangement of continents. The Atlantic Ocean owes its existence to the rifting that began in Pangaea's final days. Over the following tens of millions of years, the pieces drifted into the positions we recognize today, though the movement has never stopped. The continents continue to shift, a reminder that Earth's surface is always in motion. From a geological perspective, Pangaea illustrates the supercontinent cycle, a repeating process that has occurred several times in Earth's history and is likely to happen again. Just as Rodinia and Gondwana came before it, Pangaea's successor may be millions of years in the future. A new, as yet unnamed supercontinent formed from the slow convergence of the continents once more. Culturally and scientifically, the story of Pangaea changed our understanding of the planet. The concept of a single ancient landmass was once controversial, but the evidence it left behind became a cornerstone of plate tectonics, the unifying theory of geology. Today, Pangaea stands as both a scientific reality and an imaginative window into Earth's deep past, a reminder that the continents we know are temporary and that the face of the world will continue to change. Though Pangaea has vanished from the map, it endures in the landscapes, climates, and life that followed. Its story is one of creation and destruction, of unity and separation, and of a planet that is never still. In the grand narrative of Earth's history, Pangaea remains one of the most extraordinary chapters, a time when the world was one. Pangaea's reign as a supercontinent lasted for well over 100 million years, yet in the scale of Earth's history, it was only one chapter in a much longer story. Its formation, existence, and eventual breakup reshaped the planet's geography, climate, and living systems in ways still visible today. Though the landmass itself is long gone, its legacy is written in the rocks, the fossils, and even in the arrangement of the continents we now inhabit. One of the clearest legacies of Pangaea lies in its mountains. The Appalachian Range in eastern North America, the Anti-Atlas of Morocco, and other scattered highlands are remnants of the colossal chains that rose when ancient continents collided. Though weathered and reduced over millions of years, these mountains still trace the seams where Pangaea's pieces were welded together. The supercontinent also left its mark in the distribution of species. Identical fossil plants and animals are found on continents now separated by vast oceans, a direct testament to the time when they were connected. The Glossopteris fern, once spread across Gondwana, and the reptile Mesosaurus, found in both South America and Africa, are among the most famous examples. These patterns provided some of the earliest, most compelling evidence for the theory of continental drift. In terms of climate history, Pangaea's existence reshaped the global circulation of air and water. Its immense size produced one of the largest desert systems in Earth's history, while its breakup led to the creation of new coastlines and the establishment of modern ocean current patterns. These changes influenced evolutionary pathways, driving diversification as isolated populations adapted to new environments. Pangaea's breakup also set the stage for the modern arrangement of continents. The Atlantic Ocean owes its existence to the rifting that began in Pangaea's final days. Over the following tens of millions of years, the pieces drifted into the positions we recognize today, though the movement has never stopped. The continents continue to shift, a reminder that Earth's surface is always in motion. From a geological perspective, Pangaea illustrates the supercontinent cycle, a repeating process that has occurred several times in Earth's history and is likely to happen again. Just as Rodinia and Gondwana came before it, Pangaea's successor may be millions of years in the future. A new, as yet unnamed supercontinent formed from the slow convergence of the continents once more. Culturally and scientifically, the story of Pangaea changed our understanding of the planet. The concept of a single ancient landmass was once controversial, but the evidence it left behind became a cornerstone of plate tectonics, the unifying theory of geology. Today, Pangaea stands as both a scientific reality and an imaginative window into Earth's deep past, a reminder that the continents we know are temporary and that the face of the world will continue to change. Though Pangaea has vanished from the map, it endures in the landscapes, climates, and life that followed. Its story is one of creation and destruction, of unity and separation, and of a planet that is never still. In the grand narrative of Earth's history, Pangaea remains one of the most extraordinary chapters, a time when the world was one. If you enjoyed exploring the ancient world of Pangaea with me, there's so much more to discover. From lost oceans to the rise of life, our planet's history is full of incredible stories. Make sure to subscribe so you never miss the next journey into Earth's past, and share this with anyone who loves a good story written in stone.